Right, so there we go. Hello, everyone. So I'm going to start this presentation by saying thank you. Thank you, everyone, for joining this this event. And I'm sure that there will be more people joining in a few minutes. Many things have changed since the last time we've met in this event. So unfortunately, this time we will not be able to share drinks. There will be no barbecue, no apero. But I'm sure that we will be enjoying this event, in this new format, because tonight I'm thrilled and very excited because we have two superstar speakers. The one and the only Dave Farley, who will be speaking about continuous delivery for machine learning, and Emily Gorcenski, lead data scientist at ThoughtWorks, who will be speaking about the philosophy of data delivery. But before passing the mic to Dave, I also want to say thank you to Octo for helping us with the logistics of this event. And as you may notice, and I said earlier, this session will be recorded, so you will be able to find the video on our YouTube channel afterwards, as well as some of our previous talks. So if you don't want to miss the next updates, just hit subscribe. The link to our channel is below, is right here, but you can just type crafting data science at YouTube. It will be easier to find our channel than the link. Everyone will be able to interact with our speakers and ask. You can ask your questions, and you can vote for the questions you like. We will have a dedicated QA session at the end of the presentation. So just feel free to ask your question by on the link that you can see here on the top of this slide. The speakers will answer the top-ranked questions at the end of this session. And now, ladies and gentlemen, Dave Farley.
Thank you very much. I'm going to share my screen, so let me
share.
All I've got to do is find the right window. I've got too many windows open. There we go. Right, can you see my screen okay?
Yes.
Good, thank you. So first I'd like to start with some caveats. I am not a data scientist. I've never built a machine learning system, and my interest is kind of theoretical and academic, which was largely sparked by seeing Emily speak. I saw her deliver an excellent presentation, which I really enjoyed, and we've been exchanging some emails and discussing this idea in a little bit more depth. But any of the mistakes in this are my own and not hers, and I just wanted to make those things. First, I think of continuous delivery kind of different to many people, and so when we start thinking about what continuously delivery is, I think maybe it's not what you think. At least that's not what I mean by it when I think of it. I think that continuous delivery is an important adjunct to software development. And fundamentally, the way that I like to talk about it is that the starting point is here. We're trying to optimize from idea to useful software in the hands of users, and gathering feedback from that so we can learn. And we're trying to optimize that loop so that we can do that quickly, cheaply, reliably, repeatably, efficiently, all of those good things. And I think, like much of my description of continuous delivery so far, you'll notice that I haven't said about anything about the nature of the software systems that we're developing. I think that continuous delivery is a deeper idea than that. One of the ways in which I think about it and talk about it is that I believe that continuous delivery is fundamentally about applying science, engineering principles to dealing with information systems and software. And that ought to mean that some of these principles are very broadly applicable. But I hope that's the case. And so that's really where I started approaching this and thinking about it. So continuous delivery as an engineering discipline for me is really about ideas like controlling the variables so that we can limit, in an engineering sense, we want to limit the variables so that we can understand the signals that we are getting back from whatever it is that we're doing. We're trying as far as we can to make changes in a deterministic way so that we can move forward. We want our approaches and techniques to be repeatable and reliable. We want to proceed through a series of small experiments so that we can build upon our learning and do that on a sound basis. And for that, we need to use measurement and evidence-based decisions. Again, all of these things seem to me to be true of engineering in general. They're not just about software or, human developed software. There might be some of these things that are more difficult than others in different contexts. And that's certainly the case when we start thinking about machine learning. But I think that the principles are principles that we ought to be interested in and striving to achieve. I tend to use this picture to describe continuous delivery systems for more traditionally developed software systems. And this is a deployment pipeline, the mechanism that underpins much of the thinking of continuous delivery. I talk about this in a lot of different ways in different contexts, but fundamentally what this is a mechanism, an automation place that goes from commit a change of some kind that is intended to make its way into production and ends up with an outcome that is deployable into production. So a deployment pipeline goes from commit to releasable thing in my mind. And the job of a deployment pipeline is to take that commit and try and prove that the change is not fit to make it into production. We use the idea of falsifiability to try and cast doubt on the validity of this change. And again, I think that is profoundly, deeply related to science and engineering more than as much, maybe more than to software. And so ought to be a generally applicable principle that we can take on and think about in the context of other kinds of systems than just conventionally developed software. Certainly the detail of what's in the deployment pipeline is very much colored by more traditional approaches to software development than a machine learning approach. But nevertheless, I think that the principle of trying to make change in a series of small steps and manage that progress based on fast, high-quality feedback and proceed based on the learning that we can gather based on those small steps and that high-quality feedback. So when we're thinking in terms of trying to achieve that, whatever the nature of the system, if we are serious about controlling the variables, then we've really got to take version control seriously. And for that, we need to, for certain, think about version controlling the code that we create, however it is that we created, but pretty much everything else too. In more conventional systems, we'll be thinking about version controlling and configuration management as much of the system as we are able to, so that we can achieve those kinds of deterministic ends and achieve those reliable, repeatable results. So yeah, sure, we're going to version the source code and we're going to version the the configuration of that source code, but also the configuration of the environments in which our source code operates, the environments themselves, the specification of those environments, the data that is associated with the release, the data schemas around the design of our software. In fact, everything that you can think of, as far as we can, if we're going to take the ideas of continuous delivery seriously and try and achieve these more reliably repeatable outcomes in terms of the determinism of the approach. So we're going to take version control really seriously. This list on the screen is a list of continuous delivery principles that are lifted directly from the continuous delivery book. And if you read through these, again, they say nothing really about the nature of the changes that we intend to release into production or the mechanisms that we use to achieve those releases. So I think that we can still say that in an ideal world, in a machine learning system, we'd like to be able to create a repeatable, reliable process for releasing, let's say, change instead of software, but software. We'd like to achieve that repeatability and reliability. We'd like to automate as much of this as we possibly can and try and eliminate the variance of just repeated drudgery and try and allow human beings to do what human beings are best at, which is to have inventive, creative thinking. And we want to maximize their ability to do that by automating nearly everything else. We're going to take version control seriously and try and be strict and complete in terms of our approach to version control so that we can achieve these kind of more deterministic, predictable outcomes. And we're going to do things more quickly and efficiently, many small steps rather than fewer big steps, because that way gives us more opportunities to learn, reflect on our learning, adapt and improve. We're going to do things that are difficult more often so that we can drive out the problems, understand how we can make those parts of our development process more efficient. We're going to take quality seriously. We're trying and build quality outcomes from the start, and we're going to aim to improve continuously through these many small changes. And I think these are good principles. Jez and I wrote these down a long time ago now, but I think that they stand well in terms of allowing us to kind of think about these in other contexts, not just the kind of software that we were building at the time. Another take on this is another quote from the book. Continuous delivery is the ability to get changes of all types, including new features, configuration changes, bug fixes, experiments, into production or into the hands of users safely and quickly in a sustainable way. When we start thinking about how this applies to machine learning, there's a lot of questions, and I apologize to Emily. I hope that I'm not treading on her toes in terms of what she's going to say in her presentation, but some of these ideas are ideas that I've stolen directly from her. So, machine learning models have a shelf life. As soon as you've gained some insight, it's old news. That's clearly true in terms of the way these systems work. I think it's probably more true of modern developed systems, for want of a better term, than you may give it credit for too. They are also a moving feast very often these days. Certainly, at the edges, if you think about the ecosystem that is Google or Amazon, those sorts of places, they are moving all of the time, and not just in the bits that are applying machine learning thinking. But I think it's fair to say that it's probably truer of machine learning systems than others. The sooner that you can get that insight into the production, the more likely it is that it's going to be relevant. If you have inefficiencies, inaccuracies in your release process that mean that it's going to take you a long time to get that change, you spent all of this time trying to train a great algorithm, and the game's moved on by the time you get it in place. So continuous delivery in many ways is even more important for data products than for software products. Continuous delivery for machine learning is about transitioning from research into production states. That's a direct quote from Emily, which I think is applicable. I picked up this kind of model. This is probably over simplistic, but this kind of model is a good starting point, describing the flow of machine learning development. We're going to start trying to describe some desired results, some kind of target that we're going to aim for. We're going to assemble and develop some training data, and then we're going to run that through our algorithm in a training exercise in order to try and create a model. At some point, we're going to, once we're happy with it, we're going to transition that model into production, and then we're going to be interacting with live data, making predictions from the live data and capturing results. This is a diagram of some of that process that I took from a website describing machine learning workflows. So we're starting with data management and looking at data acquisition and preparation. We're going to once we've got that to a certain level, we're going to move that into model development and training, and we're going to try and validate that and see how accurate it is based on the target that we're trying to hit. If it's not accurate, we're going to go back and we're going to play with the data some more and refine that and refine our models, run it through the training again and see how far we can get. Once we get to a level of accuracy, we can think of moving that out into production and evaluating it there. We're going to need to monitor what's going on in production and validate what's going off. We're looking out for the need to retrain, the data drifts that are happening based on the changing environment and so on, and feeding that back into the data management experimentation cycle so that we can keep monitoring and improving the models that we build, that we train and deploy. As a neophyte when it comes to machine learning, this makes sense to me as a model. I don't know what you would make of it, but this kind of made some sense. So I started from here looking at these two pictures and thought about what sorts of techniques could we start thinking about applying to help in these processes. One thing that I should have said at the start is that this is a presentation that I intend is going to end up with more questions than answers. So I'm kind of posing the questions, and that's intentional on my part because I don't know enough about it to be anything but exploratory. But thinking about it and trying to apply those sorts of principles, engineering principles, what are the ways in which we could strengthen our repeatability and reliability of that? There are some fairly straightforward things for a start. We can think about version controlling these things, the models that are generated, the input results and the training data that we use to create those models. We can certainly start thinking about that, and that in itself, from what I understand from talking to people that are more expert in AI than I, is not necessarily the way that many people work. Many people sort of ad hoc changing Jupyter notebooks and those kinds of things. That's not really what we would think of as good engineering practice in other contexts. It's certainly not what we would think of as a repeatable and reliable approach. So upping the game in terms of version control is certainly one step. Then we could also think about applying ideas like infrastructure as code, managing the environments in which some of these things operate and are deployed to ensure that we are controlling those variables too, and we're not going to get into difficulties with the environments having some impact on the operation of the systems that we generate. So that's kind of table stakes, it seems to me, to get started. That there's certainly an awful lot of complexity in terms of managing the large data sets that are involved here and dealing with those. There are some interesting technologies maybe that are able to help. So there are certain classes of storage devices that will only store the data that changes, and they will have vast stores, terabytes of data, but they will only store the bits that change, and so they can be very efficient at storing and managing data as it transits. There are those sorts of things that I would imagine being able to, those sorts of technologies that I would imagine being able to employ in these kinds of very large data sets to allow us to start to modify those data sets in more constrained, controlled ways, and still be able to version control what's going on in sensible amounts of time. The next part of the picture is this one, and again, I'm going to apply the same kind of thing. One of my animations has failed, but I'll come to that. So let's think again in terms of version control and infrastructure as code, and the way that those techniques could help us in these contexts. So first, in terms of data acquisition, we'd certainly want to be able to version control the data that we were acquiring, so that we could repeat it as we modified it and enhanced it. As we're learning more, we can kind of update it and step back to a version that happened before, and so on and so on. Similarly, data preparation techniques, as we're cleansing that data and working on that, and the scripts and so on to generate artificial bits of data in the data sets to help train our models and that kind of thing. Again, I would see that as a mix between both infrastructure as code and version control to support the tooling, the infrastructure as code stuff to support the tooling and development environments and so on, and version control to look after the actual data assets and tooling, the configuration stuff, code, and so on that we create as part of the process. Experimentation. Again, I see this as a mix of version control and infrastructure as code. Infrastructure as code to ensure that our tooling and development environments are reproducible, recreatable, using those sorts of techniques, and version control to allow us to incrementally develop our models and hone our training to be able to improve the accuracy of the things that we're creating as we move forwards. And then there are other places where we can start thinking of using infrastructure as code and helping us to control the situation and get more repeatable and reliable in the approach. So all of these environments, I think, are amenable to these sorts of basic techniques of just managing and reproducing these sorts of the environments in which we're operating, the tool sets, and version controlling the data, so that we can make small deltas and move forwards and backwards in our changes. And if we take a misstep and change the data in a way that we don't like, it's very easy to get back to where we were. These are kind of obvious techniques that we should be thinking about applying and adopting as part of the development approach, to my mind, if we're going to be able to achieve some of this, improve the repeatability, reliability, determinism, and assert some level of control over the variables that are inherent in our development process. So fundamentally, what we're trying to do is that we're trying to figure out how we can improve the feedback here. What's the scope of a deployment pipeline in this model? So I think this is the scope. Sorry, I'll step back. So we've got data management and experimentation. That's really fundamentally part of the deployment function, really. And so this is the scope of what we're looking to try and establish, some form of deployment pipeline that can go from any change to something that is deployable into production and releasable in a conventional sense. And the question then is how we can optimize that to get that quickly enough and efficiently enough. We could certainly lock these things down and version control them and use infrastructure as code to make these things more stable. But can we do that in a way that is quick enough and efficient enough to be able to sustain a useful working model in building these machine learning systems? So what is the next step? The way in which continuous delivery works for software systems is that we talk in terms of each time we create a commit, we give birth to a release candidate. And the job of the deployment pipeline is to demonstrate that that release candidate is not fit to make it into production. We're trying to use the deployment pipeline as a falsification mechanism. Could we apply that kind of thinking to machine learning models too? So in a conventional system, a release candidate is a working deployable system of some kind. I think that is very similar for a machine learning system. A release candidate is a working deployable model, and it's monitoring and alerting systems that are associated with it. I think that's very, very similar, really. The way in which we managed to achieve that model may be very different, but the deployable thing itself is ultimately a bunch of software, and that's what we're trying to achieve, a bunch of software that can carry out this useful work. So a deployment pipeline goes from commit to releasable thing. Is there an equivalent that we could imagine for a machine learning system? And this is very much, as I say, this is a straw man, and I don't think it's even close. My intention when I started the conversation with Emily some months ago now was to see if we could come to some conclusions about what would make a good candidate for deployment, for entries in a deployment pipeline that would be able to assist in a machine learning development workflow. And I don't think that we're there. I don't think that we've got that yet, but this is an initial thought. So we've got some development environments. We're going to be doing some stuff. So version control and artifact repositories, we need those in place, and they should be a pervasive tool within which all of the assets associated with generating the models, cleansing the data, establishing training targets and so on are controlled, so we can make changes in small steps. We need discoverable and accessible data. We need to be able to get hold of data assets and manage those in some controlled way. So again, we can deploy those in repeatable and reliable ways. We need to absolutely think in terms of the infrastructure environments and the experiments that we carry out in those environments, and version control those through infrastructure as code techniques and version control where there is code that we are writing. And scripts and so on. We need to be able to monitor the performance of models and capture data from production, so we can close the feedback loop from production into our development approaches and systems. And we need to monitor the model in production using we need our models to be observable, so we can see what's going on and whether our training has been effective or not. And that's it. There's a huge amount of devil in the detail here, I recognize, but I hope that it's a start for a conversation. One more thought. The best way to test model performance is to see how it performs with real-world data. So if we are genuinely being engineers, if we are genuinely applying scientific principles to evaluate that, we should be thinking about deploying multiple models into production in parallel and comparing results with techniques like A/B testing. If we had mechanisms that were repeatable and reliable in terms of being able to manage those things, control the variables, it would facilitate this approach. We'd be able to deploy systems into production. This is a well-trodden path for more conventional software. So we'd be able to deploy two different versions, target different populations interacting with the system, so then evaluate different models against one another and compare and contrast and see what makes sense for these approaches. That's it. That's my presentation. As I said, I don't think it comes to any strong conclusions. I think of continuous delivery as a genuine engineering discipline for software development, and by that I mean in the strictest of definitional terms. What I mean is the application of scientific style reasoning to solving practical problems in software. And I think that we ought to find a way of being able to do that for machine learning systems and the machine learning workflows as much as for any other kind of software. Without that, you are really just crossing your fingers and hoping that the answer is going to turn out okay. With it, you assert more control. And really, that's the message that I was hoping to make with my presentation this evening. Thank you very much.
Thank you, Dave. I will just share again the link for the questions. So just going to put the link on the chat. Yeah, so feel free to ask your questions here. So I can see that we have a few questions. Well, what I suggest is that we'll take all the questions at the end. We can just take a 2 minutes break, and then we can hear Emily speaking about the philosophy of data platform.
Super, thank you very much. And also thank you for the greatest introduction that I've ever had, Dave. I'm flattered that my name is so frequently there in your talk. But I have to give credit to my colleagues at ThoughtWorks for really helping shape my thinking in this domain. So it's not just me, but it's a continuous legacy of folks that go back to your time there, and I'm sure even before that. So what I want to talk about today it's actually along the same veins of what Dave just spoke about, but it's a bit, I want to take a step back. And the reason that I want to take a step back is because I work for ThoughtWorks, which is a digital services consultancy. And as a data scientist and a data engineer, and they're calling me the head of data now at ThoughtWorks Germany, I see a lot of clients, and I see a lot of clients struggling with various aspects of data engineering and data science. And so we often get requests like, we have a data science team and they've built a model and they're struggling to get it into production. It's been 12 months or it's been 18 months. We think we need a platform. And we kind of come in and say, no, what you don't need as a platform is you need a delivery scheme or delivery philosophy. And then the more I thought about it, the more I started looking, especially while talking about continuous delivery for machine learning and building in the pipelines, what is it that we mean when we're delivering software? So that's what I'll be talking about today, and I'll end with some very concrete examples of what we're doing. And this will cover both data science and data engineering, and the intersection of both of those concepts. So very briefly, do the typical introduction. I work for ThoughtWorks. We're a global company with almost 8,000 people now. I think this is a little out of date. All over the world, and with several locations here in Europe. But what's interesting about us is that we do a lot of writing and philosophizing around what it means to deliver software. And that's why I call this the philosophy of data delivery. And one of the publications that we create is the ThoughtWorks Tech Radar. We publish it twice a year. The next version, volume 24, will be out, I believe it will be out next month. But in the last volume that came out this spring, we put a new blip on the radar for something called declarative pipeline definitions. And this is something that we've experimented with at my client. And it's something that has really changed. It's changed our world. And this goes along with the principle of continuous delivery. And so what I'll be doing is building up this concept of what does it mean to build a declarative pipeline, and how can we use that for data science and data engineering. So as Dave mentioned, sort of the heart of any continuous delivery system is the delivery pipeline. And we might be familiar with this. Maybe some of you are software engineers. Maybe some of you are data scientists and you've never really worked in a software delivery team. And so maybe you haven't built a delivery pipeline yourself. But fundamentally what it is, it's a way to move source code into production. So we take our code on the left and it comes out of this pipeline into the cloud on the right. And we do some things like the pipeline is not just a set of steps. We gives it some configurations, maybe in some YAML. We'll throw in some security keys in there, and then a bunch of tests. And these tests are quality gates. These are unit tests, integration tests, all sorts of. There's when Dave and Jez gave their talk at the same conference I spoke at in January, they had this great slide that had like 40 different types of tests on it, and we put those all into our pipeline. And that's all fine, and that's how we deliver software. So this is the fundamental building block of how we build a microservice or how we build an application or whatever. And we're very good at this in the software space. Like since the book Continuous Delivery came out, the industry has really changed, and we've gotten really good at building delivery pipelines. Like maybe not as good as some would like to see, but if you look at where things are now versus where things were 10 years ago, it's a sea change. It's completely different. So then, that's one type of pipeline. And the awesome thing about being a data scientist and a data engineer and working for a software consultancy, and also being somebody who cares about diversity in tech, is somebody will come up to you and be like, I've got a pipeline problem, and you say, which one? And so there's a different type of pipeline. This is your data pipeline. And data engineering is essentially, as an art form, the process of moving data from one system into another system, oftentimes translating it or transforming it along the way. And so in our data pipeline, what we do is we have data that comes in on one side and data comes out on the other side. And if you look very closely, you'll see that the data on the right is slightly different than the data on the left. It's upside down data. And much like in our software delivery system, the pipeline is not just a series of steps to move data from point A to point B, but we do some things that transform it, like we write some SQL or some Spark code. We again, add in security keys and all sorts of things to manage the data. And then hopefully we have also some data tests. Fundamentally, this is what our data engineering pipelines look like. We pay data engineers a heck of a lot of money to engineer these pipelines. And most of what data engineers are doing ad hoc pipeline building. If you're a data engineer on the job market right now, it's a great time for you because everybody's looking for data engineers and nobody can hire any. So whatever you're looking for as a data engineer, whatever number you're looking for, just add a 10 to it, and that's probably what you'll get. Then when we talk about data science, we talk about machine learning pipelines, right? And this is the process of training and validating our data and our models that we build, cleaning it, processing it, getting it into a format that we can use, because ultimately the frameworks that we use for machine learning development are very fickle, and they require our data to be in very specific formats that our data usually doesn't live in. And this is the reason that many data scientists say, oh, 80% of my work is just transforming data so that I can shove it into TensorFlow or whatever my machine learning framework is, Torch, or whatever it might be. And so our machine learning pipeline is also just a pipeline. We take some code and we take some data and we run it through this pipeline, and out comes a model, right? And you would think like, okay, so maybe this is the same type of situation. And it is, you'd be right. We write some code, maybe it's some Python, maybe it's some Scala. If you're really avant-garde, you might be writing some F#. And then you do some validation, you do your k-fold cross-validation, you do whatever other technique you want to throw at it. And then out the other end comes your fancy little neuron, and now you have a model that you, in theory, can put into production. And so if we're looking at building a full stack continuous delivery pipeline for machine learning, we might be looking like doing something like this. And the breakthrough on this is understanding that really all of this is just the same step over and over and over. We're moving things through a pipeline with quality gates and some meta information, using some set of tools to get our data into a workable form in an application in the cloud. Or maybe it's not an application in the cloud, maybe it's an email that or it's a report that we email to somebody that they've paid a lot of money for. Or maybe it's a set of recommendations for our finance department, or maybe it's something that goes into a dashboard. But no matter what it is, the point of it is those specifics don't actually matter. And the great news is that there's lots and lots of tools that help us do these things. We've got DVC is this great little tool for versioning data. We've got continuous delivery and continuous integration tools like Circle and Jenkins and GoCD, rest in peace. And then for data engineering, we've got all sorts of orchestration tools like Airflow, et cetera, et cetera. If you were to take a step back, if you were to elevate yourself to the 10,000-foot view, and you were to look at what these people are doing, very seldom is the same person or the same team starting at the left and going to the right. When you look at any organization of a certain size, and usually that size is about 50 employees, nobody is responsible. Nobody can even describe for you the full end-to-end process of delivering a machine learning application. To me, this is a problem, because ultimately what this is a repeatable process with a different flavor. This is just different accents of building pipelines. And so maybe what we should be doing is standardizing that. When we think of this, if we just focus on software delivery, what is it that we're doing with our pipeline? What is it that we're actually doing? You might say, oh, well, the pipeline is to get code into production, and that's true. But what is the benefit of it? Well, we're removing ad hoc scripting. We're standardizing our deployment processes, right? We're making it easier for developers to take responsibility. We're automating testing. We're making it easier to fix bugs and roll back changes. All of this stuff, like, when was the last time, when GitHub goes down these days, it's a big deal. If you were on Twitter 10 years ago, you would, hear about the fail whale, and this doesn't happen anymore. Why is that the case? It's because we've gotten so good at building software delivery systems that critical failures that are noticeable to the user and long-lasting are exceptionally rare. And so how do we take this sort of concept? What is the philosophy behind this? Ultimately, software delivery is about taking code and turning it into an artifact that goes somewhere and does something and delivers value. So if we were to build a continuous delivery pipeline, and this is something for a side project that I took, generally it's like we're building a bunch of YAML, right? Or we're writing a bunch of YAML to serialize the steps. And this is my Circle CI config for a project that I run. And if you look at it, like, this is actually an extraordinarily powerful concept. I push code to Git, and I have this nice little file, and there's very little actual code in here. It's just a couple of bash commands. And what is this doing? This is building my entire website automatically. And I have serialized the pipeline process. I have distilled the entire essence of what my delivery process is into a handful of lines of code. And the astute reader would see that I don't have tests in here, so you're allowed to yell at me for that. But ultimately, what this is a very powerful concept. This allows me to focus on writing the project, right? Doing what I'm doing with this project, rather than doing all of the work, the scripting, the engineering to get my project into production. The problem is that this philosophy has not yet entered into the mainstream consciousness in the data landscape. Data engineering is all about writing these ad hoc scripts. I took this code from Airflow's tutorial page. I love Airflow. I work with it every day. there's no reason for code to be written like this. And yes, it's a tutorial. Of course, it's not going to be production code. But this is the type of stuff that we see everywhere we go looking at data systems. It's all of these, okay, I'm going to have an abstraction of an operator, right? This bash operator that you see. And this has some properties that I'm going to pass into it. And then I'm going to give some commands into it and maybe some parameters, etc. And then I'm going to have like this weird little syntax down, down at the bottom that maybe you can see once the controls go away, this T1 greater array, T2, T3. Like, why am I using bit shift operators to define DAG orders? That doesn't, I know why, but this isn't what we want to see. This doesn't encapsulate the philosophy of data delivery. This is writing programming. This is scripting to make things happen. We could make it look like this. We could make it, again, look like YAML. Now, I know YAML gets a bad rap, and I'm not saying that you have to use YAML, but what I am saying is that removing that engineering step has a lot of benefits. This is the Airflow example codified into a YAML syntax. What I would then do is I would write an interpreter to take this and translate this automatically into an Airflow DAG syntax with the right operators, etc. So I build yet another abstraction layer over this. The benefit of that being that I can completely test everything because I can test my framework that assembles my DAGs. The original code that we had no tests. There was nothing guaranteeing that when I push that code to Airflow that my pipeline is going to run in the right order. This way I can test that. Not only can I test it, I can test it for every future pipeline I will ever build with the same set of tests. This is extremely powerful. And in fact, on my project now, this is exactly what we are doing. We are building a data platform for an extremely complex application that is taking data from multiple different sources, from hundreds of terabyte Kafka streams to literal Google Docs that we have to API access into, merging all of that together in a very complex sequence of events. We haven't touched DAG code in months because we've written a framework that translates that all into declarative pipeline definitions. That framework is fully tested. What does that mean for us? It means that because we're not writing the code to move our data back and forth, we're actually spending more time working with the data. And so we're improving that framework. When we institute a new data source, we automate data quality tests. We can just throw in a single line of YAML saying, I want to do null checks on this new data source, and it automatically builds in those tests. This is extremely powerful and very cool. When we get into data science, the situation is even worse. This is an example that I took from Scikit-Learn's website tutorial. And this is the type of data science code that we see all over the place. Stuff that's buried in for loops. There's no function declaration here, right? There's all of this like extremely, context-specific, domain-specific functions and calls here, like set xlim, set ylim. You probably can't even see it on the screen because there's so much code. And this is, I think, part of the problem, right? Because when we think about the philosophy of what is the work product of data science, it is not this code. The work product of software is an artifact built from code. This code does not necessarily build an artifact. This code sets up a framework that requires the orchestration of multiple other tools to build an artifact. So we should be moving away from thinking in terms of I write code to build machine learning artifacts to I write code that enable processes to build those artifacts and I automate those processes. So again, this is a place that we've been before. Like I said, this is something that we've seen many, many years ago with the software engineering space. And if we wanted to bring this all together and think of software engineering or pipeline engineering philosophically in the data space, what is it that we're doing? We're looking at, in software, we're looking at writing declarative build steps. We're pushing out easy, testable code that is easily rolled back. we're able to evolve. We've even taken it with infrastructure as code as a concept. We've taken this a step forward and said, hey, we can apply these concepts not just to building applications, but to building entire systems architectures. We can tear things down and stand them back up, and we don't even care. It's just a line of Terraform, or it's a line of cloud formation, and things are very easily evolved. When we move over to data delivery and ML delivery, we want to be doing the same thing. We can build declarative pipelines using the techniques that I just showed. We can also start building in generalizable data quality tests. It's one of the biggest complaints that we see in both business intelligence and machine learning is that data quality issues lead to an erosion of trust. And when you lose trust in your data, then you stop making decisions based on your data and you start making decisions based on your instinct. This is also allowing us to make things more testable. And this is a paradigm shift from the previous way of doing ETL, which was these sort of no-code tools that integrated with Hadoop systems. So you would just sort of drag and drop your pipeline. We don't actually like to see that because you can't test things. And this also allows you to build in better monitoring. When we talk about machine learning, we can actually start eliminating the boilerplate code. I never want to have to type import scikit-learn ever again in my life. I never want to have to type import TensorFlow ever again in my life, because the code that I'm writing is almost always the same. The only things that are different are the little things that I have to do to get the data to fit into the framework. So I want to separate those steps, and all of the data conditioning becomes one pipeline step, and then the model building becomes a different pipeline step. And I separate them, and I start making frameworks around them so that I can think of my artifact not as the code that I'm writing, but the model that I'm shipping. The artifact that I create when I do data engineering is not the pipelines, it's not the Scala code, it's the data is my artifact. That's the change in philosophy. So that's all that I really have. I'll sort of end it with that, and I'll be happy to take questions around sort of what we're doing and how we're actually making this work in a practical sense, because this is very high level. And I'd love to hear your thoughts on what struggles you've had and how you've solved them. So thank you.
Awesome. Thank you, Emily. All right. So I'm going to put again the link for, yeah, you have some virtual applause. I'm going to share the link for the questions here on the chat. It seems that people have enjoyed both talks.
Do we need to go to some place to see these questions? Or
Yeah, sure. I'm going to share them right now. I'm going to share my screen. Okay, so can you see my screen?
Yes.
Perfect. Okay. All right, so here is our first question. How do you think continuous delivery version should be done in a microservice architecture where there is high amounts of interconnectivity? For instance, an update to a machine learning model output schema can have effects over many parts of the distributed system.
Yeah, so I'm going to talk about this from a conventional system point of view and not try and translate this into machine learning, because I'm going to get lost in that idea. But this is true of information. So this is true whatever the kind of thing that you're talking about. It's all about dependency management and coupling, really. I think at the level of kind of information theory that there are two fundamentally hard problems that we face all of the time, every day, when we're building complex systems. And that is concurrency and coupling, and everything else really is easy. So when we're talking about systems, it doesn't matter whether they're ML systems or whatever else. It's about managing the concurrency and the coupling in our systems to some degree and coping with that. In microservice architectures, they are a widely misunderstood architectural technique. And one of the characteristics of a microservice architecture is that a microservice is an independently deployable thing. And so if there's high amounts of interconnectivity between microservices, then versioning those independently is not the root. Is not really the microservices solution. The solution to solving microservices problems is to decouple those things. So you get more abstract interfaces between the components, so that each one can vary more independently of the other. That's the value of microservices. So fundamentally, there are two approaches, and I'm trying to keep this in broad informational terms. This is just as true of human systems as it is of computer systems. There are really two models. You either put everything together, and therefore you can have a highly coupled system, but everything is evaluated together and tested together and deployed together, and work carries on together. Or you separate things out, and then you have to do things to manage the interfaces between those different pieces of work. So to my mind, continuous delivery is grounded in that. So a sensible scope for a deployment pipeline for a continuous delivery system is either an entire system, in which case we're going to build, test, and deploy everything together, or it's an individual service, in which case we're going to build, test, and deploy everything independently. In which case we need other techniques than testing to evaluate, to keep those things talking to one another. We need then to be thinking about creating those more abstract interfaces that allow change to happen in different parts of the system. And I think that's kind of a fundamentally true idea. I don't think that's specific to microservices or even software. I think it's just true of information. I think it's so. I think that the same thing is going to be true over an ML model. So either you can find ways of separating the pieces or not, and probably not in many cases for ML systems. I don't know. So the scope of evaluation needs to be something that is coherently a whole deployable unit of thing. In this case, I agree completely with what Emily said, which is that I think that the target is that the stuff that you do along the route is just work that you do to get an outcome, which is to generate a model. And that's kind of true in software as well. If you abstract the thinking a bit, that's absolutely true. We have compilers in the way and build scripts and all those sorts of things. Those are just mechanisms to get to a functioning piece of behavior that can execute on a machine. And both of the outcomes in that sense are the same. And so many of the problems are related, I think, in terms of managing this.
If I can also jump in here. So along those lines, I think Dave's bringing up a good point in that this is an interface problem, and it's not just a technical interface problem. The way that we manage those interfaces when we're talking about parties and people, it's with contracts. And where I've had success is actually just building in contract testing as a first-class component of our ML system. And what this does is when you have these contracts with whoever's integrating with your ML system, if you don't have a contract with them and your change breaks them, it's not your problem, it's their problem, because they're doing something. They're integrating with the system they haven't agreed to a certain service level of. If you do have those contract tests, and then those contract tests will prevent you from deploying a breaking change. And if this is very painful, this is good, right? Because like Dave said, do things that are painful more often. And that will tell you something about what you're doing. And so if this is a very painful change, because one little change to an output schema now affects like 3 systems, and then each of them 3 downstream systems, right now that should be like setting off some warning flags that you need to do blast radius management. Yeah. Because what's going to happen is it's not just your output schema that is going to affect your systems. It's telling you that there's this degree of coupling that's happening, and like your reliability level is decreasing and your risk profile is increasing because you have the power to institute these ripple effects in your architecture. So we should be doing certain blast radius management and removing those sort of couplings. And contract testing is one way of doing that.
Yeah, and that's widely used in sort of more conventional microservices style architectures too, for the same reason.
Right. Thank you. I don't know if Fraud is still here, but if you're here, does this answer your question? Yeah, perfect. All right, going now to present the next top-ranked question. Okay, I think this question is for you, Emily. Can you tell us a story about the client with whom it was the most difficult to explain and shift to automating delivery?
The answer is no, and not glibly. There's different degrees of difficulty, and it depends on the starting point that they're at and what it is that they're trying to accomplish. So I'm sort of working on this other talk at the same time that I'm giving. If I may pitch a talk that I'm giving at a free online conference on Tuesday called Percona. It's about data reliability engineering, and what I see is a pattern of difficulty that happens with data. And what's interesting is that this pattern repeats itself regardless of the scale of an organization. It's something that I've seen at fast-growing 100-person startups to 100,000-person enterprise clients. And it's because fundamentally we have convinced ourselves over the years that certain architectures are best practices. And as our technology has evolved and as our thinking has evolved, those best practices are no longer best practices, and now we are living with the consequences. So I've had startups that are more difficult, where you think, oh, they've got infinite money and no legacy, that are way more difficult than doing a lift and shift in an enterprise client. And so it really depends. I can't tell you which is the worst for me. I can tell you the ones that have given me the grayest hairs. And that was really just trying to get, it was all organizational. It was trying to get people to understand that, you can't treat data teams as IT help desk teams. They're not just there to do the data pull problem. Sort of like classical thing, like, oh, can you pull me data that tells me how many left-handed people in Berlin buy my shoes? And it's like, no, that data, there's no table that has this data for you. So.
Right, thank you. Yeah, the next question actually, it's not mine. I just copied it from Vincent, and I think it's for both of you. The question is simply, how can we version data sets? So
I can. So this is a common continuous delivery problem. Part of my background before I started consulting and talking for a living, I used to write real software, and I was involved in building trading systems, and those are environments where we process vast amounts of data. So I was involved in building a high-performance financial exchange, which was generating in the order of about 1 terabyte of data a week that we had to keep forever. And so it's a different kind of problem, but you still got to. It's still a problem of data and scale, and it doesn't seem to me that there's fundamentally any difference in that respect. It's just a matter of the amount of stuff that we've got to cope with. And the real answer is that you use all of the techniques that you can. So there are different aspects of data that you need to think about depending on what you're talking about. At some level, you probably need to understand some degree of structure. So there is some, I don't necessarily mean this in a relational sense. Maybe I do, maybe I don't. But there's some level of schema. However you store or manage your data, somewhere or other, implicit or not, there is some notion of a structure that allows you to layer, something that allows you to convert data into information. So you need to be able to understand that, and you need to be able to manage that. Sorry, go ahead.
That's right. So I talk a little bit about data versioning. Sometimes there's two parallel problems here. One is, as Dave mentions, the schema management issue. How do you handle schema versioning? And how do you identify compatible versus incompatible schemas? How do you roll back? Like, how do you identify when you can roll back from one schema to another, or if that's a cliff, right? Mm-hmm. So if you have a field that you now separate into two fields, or change a field that changes its meaning, you can't roll back over it. And so in the database world, we started talking about up deploys and down deploys, and then all of a sudden it's like, this was like back in the Rails era, everyone was like, well, you can't do a down deploy anymore. So you just kind of roll forward all the time in data. Yeah. And that's what's encoded in tools like Flyway. It's really, yes, Flyway has some rollback capabilities, but in practice, you messed up in V178, then you just write V179 that undoes what V178 does. In a practical sense, there's tools like Pachyderm and DVC, which I find really useful for machine learning. I love DVC for small scale problems because it gives me very little functionality over what I normally want. One issue that I see in data science is that all of these tools try to do too many things. DVC just tries to solve the versioning and reproducibility problem. So tell me, what is my data set? Give me something that I can hash and put in my Git repository. Let me link it to my object stores, and then let me encode the steps necessary to move that data into a working place. So it solves that very nicely. There's some other tools coming out. So MLflow, I think, is building it, or already has a repository tool for doing artifact management. Databricks has the Delta Lake capabilities built in. You can also build a Delta Lake on S3 if you're very clever and you're using Parquet and stuff like that. So all sorts of really interesting stuff that you can do to version data.
Thank you.
The other thing, one more thought just to kind of throw into that mix is I am increasingly of the opinion that a delta-based approach to almost all information systems is a healthier approach. And as Emily said, you can kind of take the roll forward sort of additive approach to data, and you just do that as a series of little delta changes, and keep track of all of the deltas for history, and occasionally snapshot, but allow you to replay those deltas in sequence, and you can kind of move forwards in time to different versions of the state.
The challenge with data versioning is that when you have data versioning, you have your sampling, what I call your sampling, which is your actual values. That can change over time without a schema change. So for example, you could be selling products in France, and then next year you expand to Germany, right? So your distribution has now changed. The statistical properties of your data have evolved, but your schema has not. You can also have schema changes that happen independent of your statistical distribution. So those two things can happen concordantly or at different times. You can also have code changes, and this is where it gets really tricky, because now you need to keep your code changes with your schema changes and your data changes, because if you don't update your code, then it doesn't work with your schema, and so on and so forth. And this is where it gets challenging, where some of the things like the Delta Lake models don't give you an artifact that you can link to your source control And so now you have to solve that problem. And nobody that I have found has solved that problem effectively. Not yet, at least. We're still young in this field.
All right. Next question. It's by Constantina. Hello, Constantina. So the next question is, when deploying competing models in production for A and B testing, for A/B testing, how do you ensure that the A and B datasets have the same distribution?
Oh, one way that I could imagine that you could do that is the way in which you do that for more conventional software is that you just fork the data stream and send it to two different models. You could just do that. So you could have precisely the same inputs going into two different models and see how that plays out.
Yeah, I think it's sort of the typical problem when you're running any sort of multi-arm bandit. Like, how do you actually ensure that the traffic going into one arm is of the same statistical properties as the others? The law of large numbers generally applies here if you're doing it randomly. Like if you're doing it randomly with traffic, then over time you have some good guarantees. If you're not doing it randomly with traffic, if you're doing it with, say, you're randomly selecting users in your system to deploy system A and system B to, at that point you really just have to ensure you have to have an idea of what features you're looking for, which means that you have to do some model discovery, and then you have to validate that before you deploy it, or at least have some way of quantifying those distributions vis-a-vis those features. So it's a lot more work, perhaps. But generally, as with anything with statistics, if you have enough volume, you can usually just hope that it all washes out in the end.
And it's a similar kind of problem to any other statistical problem, really. So you could say, I don't know, about medical trials or something like that, capturing the data. It's not a different problem. So you've got to manage the cohort, and you've got to try and make sure that you eliminate as many variances as you can in the data sets from that point of view. I would imagine it's the same kind of thing.
Mm-hmm.
All right. Next question. Are environments like Jupyter Notebook actually counterintuitive to effective continuous delivery as a result of the lack of structure they ask of the developer? Can notebooks be integrated into the CD pipeline?
My answer to that is this is an anti-pattern, and it is an anti-pattern that I am seeing with alarming frequency. This was such an anti-pattern that at ThoughtWorks we put this on the radar under hold a couple of volumes ago, which we very rarely put things in hold. Netflix wrote this blog like 3 years ago or so, where they're like, check out this awesome thing where we productionize our notebooks. And it was, look, Netflix engineers are brilliant. I don't want to take away from them, but most organizations cannot pull off what Netflix pulled off. And I've seen a lot of organizations try, and I've seen multi-million-dollar failures in doing so. Maybe the technology will get there, but we still see that this is solving the wrong problem. Notebooks in production is solving the problem of data scientists not writing production quality code and trying to give them, trying to solve the production problem by catering to their way of working rather than reshaping their way of working to cater to what we already know to be a set of best practices. And so I still think there's a lot of clever engineering out there, but for me, we really want to take we want a point at which we take the code out of the notebook and put it into a module, and it just will require data scientists to learn better coding practices, frankly.
I can't talk to this directly, but what Emily's just said reminds me of a problem that I am more familiar with. I do a fair amount of consultancy with often large organizations, helping them improve their software engineering practices. And for some reason or another, a significant minority of my clients have science as part of their problem domain. They build scientific instruments or medical devices or whatever else it is. And my observation is, without being too rude to the audience this evening, my observation is that one of the problems with scientists and physicists is that they assume that software is simple, and therefore they don't pay enough attention to it, and they don't listen. They don't think about it in terms of having to apply different kinds of problem solving skills and different kinds of disciplines. As Emily said, over the decades of evolving software development practice, we have learned to do some things better. We've made all of the mistakes that you're talking about in this context, but we found ways of avoiding those and organizing our work in different ways. It means that you've got to apply certain levels of discipline in order to be able to develop software that has certain identifiable properties that count as a quality outcome. Good software is modular, it's loosely coupled, it has good separation of concerns, it has high cohesion, it is abstract, it has lines, seams in it that we can distinguish one area of function from another. All of these good things, we kind of know some of this stuff. Good software developers use these ideas as tools to build better software. And what you are describing sounds a lot to me like my experience of working with physicists who just assume, oh, coding, that's just the simple part of joining together. That's just not true. And however smart people are, you've also got to learn the disciplines of the tools and the techniques that you're using, and software brings some new challenges.
I can share a quick anecdote. This was a few months back. One of the teams I was working with on my current client, they were working with a modeling team who had built a model. The model was working great, it was fine. They needed to adapt this model to a specific use case. And so there were some changes in the data that this model needed to act on. And so the model was built in a notebook, and it was built actually in like this multi-cell, about 1,500 lines of combination of SQL and Python code that was connecting to a database, crunching, pulling it into a data frame, doing some crunching on it, emitting some results, and that was the forecast. And so this team, they took this notebook and they tried to adapt it for their own use cases. And then they came to us and said, okay, here's your product requirements in the form of a notebook. And we said, okay, this is not what we asked for, but we'll work with it. And so we built it into our pipelines, into our fully testable data engineering workflow. And this is a week before launch of the product, and the numbers don't match, and we can't figure out why. And I was up till midnight, 5 days in a row on my birthday, trying to figure out, why is this not working? We missed the launch, it's okay because we did have a fallback plan. So after we had the retro, we came back and said, okay, what do we need to do differently? So we got all three teams in the room. I said, we need tests around this data. We need to understand what is working and why. Can you go out, make up some data? I'll make up the data for you. Just tell me what the value should be. So the data scientist went back and wrote up the test, wrote up the values, put it in an Excel sheet. That was fine. It took me 2 hours maybe to take all of these test conditions and turn them and put them into our testing framework. Once I had that, it took me less than 15 minutes to find the bug. So the value of doing this the right way, test-driven functional decomposition. I mean, this was the difference of 2 hours of testing plus 15 minutes of bug fixing versus 60 hours of labor by 3 teams, 10 people total, right? That's the value change that you get from this. And so I really push for this. Like, if I know writing tests sucks, but it saves you so much time.
Yeah.
Thank you, Emily, for saying that. I think that the community here is looking for some experience sharing like this. And I'm going to share one question that seems to be funny. Emily, what is stopping you from going full drag and drop from the declarative code and maybe include some building blocks that allow testing?
So with the drag and drop, the problem is that drag and drop systems are, one, difficult to version control. Two, require you to have a completely new tool and interface to use them with, which is fine if you've invested in that. But what we see is that builds you into vendor lock-in. Like if you're using Talend, which is a fine tool, you're stuck with Talend and you can't then transition it into something else. With the declarative code, the benefit of it is that it's easy. You can keep it in Git. Anyone can change it. You can track the changes over time. You can port it to a new framework. You can port it to a new language. All of those things are possible with it. And it's also easier to visualize. So, there's sort of a trade-off between like the high code, like I said, the scripting, your pipelines, we don't really like that. And the no code, we really don't like that either. So what is the right solution in our opinion here in 2020? And in 2025, I'll probably be giving this talk again and being like, no, that's garbage, don't do that. Right now, we believe in declaring things and making it clean, giving it a clean interface and a clean schema, and then using that to build up whatever framework you need in whatever tool. So right now, the pipelines that we have in our YAML, they're portable. If we stopped using Airflow tomorrow, we could just write a new framework and we could use NBN, or we could use some other tool to build those pipelines. It would, we'd have to do some adaptation, but we could still do it.
I think there's an interesting thing here. Again, sort of just talking in general about information. What would you think about a system that allowed you to write a book with drag and drop? I think it's unlikely that you're going to write a great work of art if you do that. And software is as creative a process as that, and has more complicated constraints. Software is differently fragile to writing a book, because books are interpreted by human beings who have these amazing computing devices that can read garbage. You can leave out half of the letters and still read, get useful information out of that. You can't do that with software. So we are more constrained in some ways, but equally free in other ways. And so I think there have been, in software development in general, not just in machine learning, there's been a lot of attempts to try and change the level of abstraction. If you look at the oldest computing device that I've looked at, I know that there are older ones, but is the Hollerith machine that did the census in the early 20th century in the US. You can write the algorithm for the Hollerith machine in SQL, and it's completely understandable to a modern programmer. It's working at the same level of abstraction that we talk about and use day to day, every day. There's something fairly fundamental about the level of detail that we need to express when defining behaviors in computers. And I don't think that changes very much. And that is captured best by far in text-based languages, I think, to my mind. And it gives you the ability to test these in intelligent ways, in the way that Emily was describing.
Yeah, you see the power of this approach whenever you have to debug a critical incident, or whenever you have to do sort of the archaeology on a problem. When you're searching through your GitHub repo, and you can see the change of how a pipeline step was formed and grew and evolved, and what decisions were made. I mean, it's really a matter of minutes versus hours for finding problems. And I think that's a real power to it. We have to engineer assuming things will go wrong, rather than engineer assuming that what we're doing is the right thing. And so, in the reliability space, we say that, mean time to recovery is better than mean time between failures. Mm-hmm. And so that's part of that optimization.
All right, maybe hopefully we'll have time just for two last questions. So the next two ranked one is this one. Emily, we're a small AI startup with a development team size of 3, and we are currently building our machine learning pipeline from the ground up. What kind of tools would you suggest for small teams like us to use to get the pipeline up and running from end to end?
So it's hard for me to answer that question for you without understanding, your data sources and your skills. But Airflow is not a perfect tool, but I have found it really easy to work with. And like I said, it has its problems, but I find it, there's a lot of frameworks that are starting to come out. Like there's a tool called Airflow Declarative that is allows you to wrap Airflow operators in a YAML-like syntax, and you can build your pipelines with that. And then the challenge is, you have to run your Airflow instance somewhere, and then there's some quirks to setting it up. Like you have to stand up a backing database to like keep its to persist its connections and variables and stuff like that. But honestly, like you can do it in a weekend, because I know that because I've done it in a weekend. And you're probably much smarter than me. So.
Right. Maybe we'll have time for one last question. There we go.
I don't work for Apache, so I'm not selling Airflow. I found it to be a really convenient tool. And actually, I've even tried building data pipelines in Circle CI, which works to a very small extent. I don't recommend it.
All right. So last question from Charles. Models are often the most important artifact to get into production. Unlike conventional software engineering, they are more difficult to falsify, as you would do with a test suite in a conventional development. When monitoring models, are there any techniques or intuitions for falsifying model predictions?
Yes, but no great ones. Well, I'm going to go off the rails a little bit here and say that actually this is one of the oldest techniques in the book. We figured this out. So my background is actually as an aeronautical engineer. So I studied computational mathematics and aeronautical engineering for my undergrad, and worked as a control systems engineer for a decade before realizing that I was doing the same thing as data science. And so I started calling myself a data scientist, and I got a 25% raise. But in the control system space, we do anomaly detection, and anomaly detection is means a different thing than what it means in the data world. And we have a systematized way of doing that. And I would love for somebody, because I don't have the time, to write a system that does constrained Kalman filtering on a closed loop microservice architecture, and is able to falsify and detect anomalies in models and their predictions ahead of time, because you should, in theory, be able to measure the error or the residual between the observed and the predicted effect with some lag. That is the complex solution and would require a team of many people and a lot of time to do. As far as the simple solution for falsifying models, the easiest thing to do is to run multiple models in production and to compare them against each other and to see if they're within the same ballpark. You can do this with sampling. You can also do this, you don't have to do it online. You can also do it as a batch process, say, as a nightly job. This is part of where the monitoring and logging comes in, to verify that the distributions of the outputs of your model are roughly what you expect. And if they're not, you should raise an alarm. So that's the simple question, is that you have to apply more, in either case, you have to apply more complex statistics to the problem.
I'm going to go in a slightly different direction in thinking about this. So thinking about this from a point of view of, science, this is just a generally hard problem. So if we were physicists looking at physical systems and trying to come up with problems, trying to figure out how you can falsify ideas, is part of being a scientist. and it's a difficult, complicated problem. I think it's a matter of believing that that's the right thing to do, and then working really hard to try and be inventive and creative to try and come up with the experiments that you want to carry out. I can think of dumb examples from the kind of folklore of machine learning systems. Things like, if somebody had thought to try and show the thing that was supposed to identify the machine learning system that was supposed to identify tanks, pictures, that weren't all at night time or whatever else it probably would have worked better. So just thinking about, what are the things in my data set, what are the things that are likely to be, that it could be misinterpreting. Something that Emily said before is that real engineers think about the ways in which things can go wrong at least as much as they think about the ways in which things can go right. So if you've got data to train an algorithm, thinking about what could there be in this data that's going to mislead the model, and it's going to mislead the training mechanism and end up with the wrong model. But what kinds of things could I imagine going wrong? And then trying to think of the data that you could put in to see whether that was the case or not. And I think it's that kind of thinking. I'm sure what Emily's talking about from a control systems point of view is correct. But I also think that there's this point of thinking experimentally, thinking like a scientist or an engineer, and trying to apply that kind of rational approach to problem solving.
Right. So I think I think that we'll end up here, and it's just time to say thank you, Dave, thank you, Emily, for the presentation, for your time. It was fun, and thank you for all participants that have attended this event, the ones also that came earlier, and also the others that stayed until the end. This session was recorded. We'll share the link soon, and hope to see you again in another event. Thank you very much.